Hi, in this video we would like to know about the transistor switching characteristics. As we know that one of the application of our transistor is switch. So usually the switch can be used in digital circuits or where we want to provide control on certain parameters. In such cases we can use these switches. So generally the transistor what we are using that will operate in three different regions: cutoff region, active region, and saturation region. But for a switching application we need to operate our device in cutoff region or saturation region only. That means when transistor acts as a switch, the device is either in cutoff region or in saturation region. So the switching action of the transistor is identified when it changes from cutoff to saturation or saturation to cutoff. So usually if the device is in cutoff region, we can say the transistor will act as a open switch, and when the device is in saturation region it will act as a closed switch. So when you are changing the device from cutoff to saturation means we are changing our switch from open switch to closed switch. On condition we are representing. Similarly, when the device is moving from saturation to cutoff, that means we are changing the device from closed switch to open switch. So you can indicate as a off condition for that particular switch. So if you are observe our basic transistor circuit, so the input what we are applying for a transistor, if that input is less than VBE saturation, our device will be in the off state, and if in Vin is greater than VBE saturation, our device will be in on condition. Now let us see here, when for example let us assume when you are applying Vin is greater than of VBE saturation, so our transistor is in on condition. That means whenever the base potential, base to emitter potential is greater than VBE saturation, the device will be in saturation region. So if the device is in saturation, the amount of current flowing through the device can be identified with help of this expression: IC equal to VCC minus VCE by RC. VCE is the potential across the collector to emitter terminal of the device, and VC is the supply what we are given. So if the device is in saturation region, the amount of potential drop across collector to emitter terminal will be very minimum. It's approximately VCE saturation. So in that case, you can identify the amount of current what we are passing through the device. If VCE is the minimum, then the IC value what we are calculating or what we are evaluating is the maximum one. It means where the device is in on state, the current drawing through the transistor is maximum. Now when you are change the input, suppose let us assume we are change our input from V in, the input which is V in is less than of VBE saturation. If V in is less than VBE saturation, then the transistor what we are using, that will move into cutoff region, because if the input potential is less than minimum potential, then device will went into cutoff region. So if the device is in cutoff region, it will act as open switch. So when the device is acting as an open switch, the current passing through the device will be almost zero. Why? Because if the device is acting as an open switch, the potential drop across the collector to emitter will be the maximum. That means across the collector terminal you will have a maximum potential. VC is maximum. So according to this equation also you can identify when VC is maximum, the IC what we are getting will be the minimum value. So in that case, when the switch is in off condition, that means when the transistor is in off condition, the current to the device will be almost zero. Now you can identify these things from these graphs. So in this graph we are identifying how much amount of the current we'll obtain when the device is in on, and how much amount of the current we are when the device is in off state, and what will be the collector potential. Those things you can clearly observe in this graph. So for example, let us assume initially the input what we are giving is 0. That means we are going to apply the potential 0 volts. So when the input is at 0, as we are considered that as long as our Vin is less than VBE, the device will act as open switch. So during this open switch condition, the current what you are representing will be 0, and at the same time the collector voltage what you are getting is approximately VCC. You are indicated as a maximum potential. That maximum can represent as VCC. And whenever we are changing our input from 0 to V, it means our input is suddenly changes from 0 to V. So this sudden change in our input will not reflect at our output. Input may be changed, but the device characteristics instantly it cannot change. So previously it was in cutoff region when we are applied our input at 0, but as we are changed our input from 0 to V, then it has to move from cutoff to saturation region. So the sudden effect or sudden change in our input, that will not affect our device instantly. So it required a time period to change its current from 0 to a maximum. So when you are changing your input instantly, the time required to change the current through the device from 0 to 10% of its maximum is called it as a delay time. So usually this delay time is to represent to change the, or you can say it is the starting time of changing the behavior of characteristics. So if you are observe this graph and you are changed our input from 0 to V, it required a certain time duration to change its value from 0 to maximum value. So that time we are indicating as a on time, turn on time. So this turn on time will also be represented as a sum of delay time plus rise time. This delay time is used to indicate as the time required to change its value from 0 to 10% of its maximum value. You can observe the definition also. The time interval between the instant of application input pulse and output current to attain 10% of its maximum value is termed as a delay time. That means when you are applied an input, the output current to reach the 10% of its maximum value, 0 to 10%, that time we are indicating as delay time. Now the rise time, what you are representing, be indicated as a change in collector current from 10% of its maximum value to 90% of its maximum value. So this time we are indicating as a rise time. So if you observe the definition, rise time is defined as the time required for the output current IC from 10% to 90% of its maximum value. (10% to 90% of its maximum value). So the total time what you are representing will be considered as delay time plus rise time. You can observe here T on equal to TD plus TR. The sum of the delay time and rise time is called as a turn on time. And now as we are maintaining our input at a constant potential, then the collector current what you are getting will also be at constant. And at the same time, if you are observe the collector voltage, at what rate the collector current is increasing, in the same manner the collector voltage will be decreases. And when the collector current reaches to its maximum value, collector voltage will also reaches its minimum value, VCE saturation. Now suppose if we have changed our input from V to 0. So when you are changing our input from V to 0, that represent the condition of V in less than of VBE saturation. So when VE less than VBE saturation, the device will act as an open switch. So when the device is acting as an open switch, already we discussed that the collector current must be 0. But if you observe the graph, instantly we are not changing our collector current from maximum to 0, because when you change our input, the device has to set the device required certain time period, change its characteristics from saturation to cutoff region. So in saturation region, the current through the device is the maximum. That means when the device is operated in saturation region, some charge carriers we are accumulated in our device in the regions of our transistors. Now when we are change our input from V to 0, the accumulated charge has to discharge now. That means you can say some charge already we are placed under the saturation region. Now when you are able to remove that charge, then only it's possible to move our device from saturation to cutoff. So the time required to remove the accumulated charge is called as a storage time. So if you observe the graph, this time from maximum value of IC saturation to 90% of its IC is called as your storage time. So you can observe the definition also. Storage time is equal to the sum of the time taken to remove the excess charge stored and the time taken by the collector transition capacitance to discharge to 90% of its maximum. That means the removing of its storage charge, or which is the excess charge what we are represented, and to reach the value to 90% of its maximum value is called as a storage time. So the total off time what we are representing, that means when our input is changed from V to 0, the total time what you are representing is called as a off time. So now that off time is considered as sum of storage time plus fall time. This fall time will represent the time required to change the output from 90% of its value final value to 10% of its final value. So that we can identify as fall time or TF. So this total time, turn off time or off time of the transistor can be represented as TS plus TF. Now if you observe our graph, when the out collector current changes from IC saturation to 0, at the same time the collector voltage will changes from VCE saturation to VCC. Means when the device is in off state, the collector potential will be maximum. Now if you observe this, turn off time is made up of storage time and the fall time TF. So TF off equal to TS plus TF. So if you want to use our transistor as a very fast switching, then the turn on time and turn off time must be in the order of nanoseconds. So the on time and off time of a device must be very short, then we can use the device as a very fasting acting switch. I hope you understand the concept of the switching characteristics of transistor. Thank you.